So we want to talk about Poincare duality. So we start with the manifold M, which is R orientable and closed. So for such a manifold, we have isomorphism between certain cohomology groups and homology groups. So let us write this down clearly. So we start with the manifold M, which is R orientable and closed. It has dimension n. That is local chart is Rn, and we have the following isomorphism. Now, in order to establish this isomorphism, we have to talk about cap products. So we have to define something called cap product, but before we can do so, we will first recall what a cup product is. So for a cup product, you took a cochain in CK, then you took a cochain in CL. We ended up in the cochain part CK plus L. So let us write this down clearly. So this we ended up in part CK plus L. So now we change our point of view a bit. So we should regard this cup product as a function acting on this map psi. So I'm taking the first one, calling the first one as phi. So consider this as a function acting on psi. And how do we deal with this function? So basically, we fix the first part, and then this first part with the cup product acts on the second part. So let us make it more clear. So we are taking cochain CL to CK plus L. That is, take an element of the cochain psi to the cup product, by fixing this element, the first element phi. So we want to build a relationship between this map and the map between homology groups, which obviously has the arrow in the opposite direction. So here you take a element alpha of the chain complex and take it to a cap product of something. So notice that the second element here is fixed. So we have to define this cap product. So first notice the kind of duality. So in both the cases, this first element phi is fixed, and that we have to keep in mind. So let us now start with defining the cap product. So first we have to take a representation of element alpha. It after all lies in the chain complex. So it lies in the K plus Lth part, and you already know that elements of CK plus L, the chain complex, have to be singular simplices of dimension K plus L. So it is just the singular simplex to sigma, the singular simplex. So now let us define the cap product. So obviously instead of alpha we are going to write sigma, and these are alpha and sigma are used interchangeably because alpha is nothing but represented by sigma. So this is the definition. So phi acts on sigma, but sigma restricted to the first k parts, obviously because phi is element of cochain ck, so it can only act on the first k parts. So after it acts on it, it spits out a number in the ring R. Now rest of the elements, because sigma acted on delta k plus L, so we still have k to k plus L remaining. That remains like that only. So you can immediately see that we have gone from k plus L to CL. Yeah, so you can see the map already defined. So now we want to talk about this duality. So the psi here, which I have just written, the psi is nothing but a cochain in CL, and you have already seen sigma cap phi is part of CL. So we have to prove this result. So this duality we have to prove between the cap product and the cup product. So this follows very trivially. To make things clearer, I will write this first part as 1 and the second part as 2. So we just apply phi to this map, sigma cap phi. So apply psi to the map sigma cap phi. So this is phi of first part and the phi or psi of second part. So what is this? I is nothing but an element. So this will just be phi of or psi of I is just I for the first part, because it is just an element in the ring. So so this element psi does not do anything because it's just a map to the ring R. So yeah, now you just look at the product and you can see the result. So yeah, it's nothing but writing down. You only have to notice that psi of I is just I, because psi is a cochain complex, it's part of the cochain complex. So acting on an element of ring R, it will still give you element of ring R. So you just get the first part. So now we want to change the terminology and write it in this format. So yeah, so we have copied the top to bottom, and here also top to bottom. Yeah, we are rewriting it in this form so that it is clear. So this is the duality between the cap product and the cup product. We want to show the following map. We take part of the k plus L part of the chain complex. Then you take kth part of cochain complex, and then you end up at the CL part. Here the L should not be superscript but subscript. Yeah, so this is what so that L where it lands, the cap product should be CL should be subscript. So it lands in the chain, not the cochain. So we want to take this cap product and talk about inducing this map. Yeah, I'm just replacing C with H. So chain with homology and cochain with cohomology. So before we can do that, we have to talk about the boundary maps. Yeah, so what is the boundary map? So boundary map is obviously delta applied to alpha cap with phi, and we will just use the identity on the previous slide to show how this works. So yeah, the boundary map is needed to define the homology or the cohomology groups. So yeah, so the first part is CL, L in the denominator, and phi is part, or psi is part of the cochain complex of LF part. Now we use the definition of delta. So delta psi, now notice that delta psi is as good as delta, the definition of delta psi essentially, the first equality comes from the definition of delta psi. So yeah, you just have to think about it, that application of delta is nothing but application of delta there on the left hand side. So notice that we have CL to CL plus 1. Yeah, so notice that how we have increased in degree for the cochain and decreased in degree for the chain. So now we just apply the formula from the previous slide, interchanging cap and cup product. Now here we want to apply the formula we have derived in lemma 3.6. You basically rearrange what is given there so as to obtain formula for phi cup with delta psi. Yeah, so take that formula and plug it in here. So you will have minus 1 to the power of k, and just now we'll just go through the motions. Now just interchanging cup and cap products and using the definition of deltas. So now we change the first term here, we use the definition of delta. So that is now, instead of cochain delta, we will apply the chain delta. Yeah, so chain delta on the first part. Now this we have seen multiple times. I mean, this is what the definition or the relationship between chain delta and cochain delta is. I will just copy the second part as it is. So now the interchange of cup and the cap product as on the previous slide. So this holds for all psi belonging to the cochain CL. Yeah, so now we do have some formula for the boundaries, and this formula is what will essentially end up defining the homology and the cohomology groups. So it holds for all psi belonging to the cochain CL, and this chain, this small CL, is a free R module. So this is the following map that we get. And this is what we will use in the next slide to define the relationship between homology and cohomology groups. So now we want to talk about induced cap products, but before we do so, we have to define certain relations which will make sense in the induced cap products when we talk about homology and cohomology groups. So we will first write down the relationship which we deduced on the previous slide, that is the chain delta sigma cap phi equals to plus minus and these two terms. And the first of our, so we have three cases to consider. In the first case, we will talk about a cycle sigma and a co-cycle phi. So cycle sigma means delta sigma is 0. So that means the first term on the right hand side in the first expression of the slide, that is delta sigma cap phi, this is 0. Now the second is cap product of cycle and a co-cycle. So sigma cap phi, the left hand side is nothing but where sigma cap phi, sigma is a cycle and phi is a co-cycle. So that means delta phi is 0. So this means the term sigma cap delta phi is 0. So therefore what we get is, if you take a cap product of a cycle and a co-cycle, what you get is delta of that is 0 because the right hand side is 0. Now cap product of a cycle, then again delta sigma is 0. So that means the first term on the right hand side of the topmost equation is 0 and a co-boundary. So co-boundary means cycle and a co-boundary means sigma cap delta phi. So what we have remaining is the second term. So if you take cap product of a cycle and a co-boundary, you get a boundary. Yeah, why a boundary? You see the term boundary refers to left hand side of the first line. Yeah, because boundary comes from the delta of something. So again, the right hand side, the only expression remaining is the last expression, which becomes equal to delta times something, which is a boundary, because the delta on the left hand side is a chain delta. So the last thing which we have to check, so we are only talking about boundaries, co-boundaries and boundaries and co-cycles. So why is it so? That will be clear in a minute. So you have a co-cycle, so delta phi is 0. That means only term remaining on the right hand side of the first equation is delta sigma, which is a boundary, and phi, which is a co-cycle, and this is a delta of sigma cap phi, so it becomes a boundary. So thus we have a induced cap product. Yeah, so this cap product, obviously this cap product which I am going to write would involve homology and cohomology group. Notice that homology is preserved because cycles and boundaries are preserved, and cohomology is also preserved when you take it across the arrow because cycles and boundaries are preserved. Yeah, so that follows from 1, 2, 3 that this map makes perfect sense. Yeah, you take a cycle and a co-cycle, you get a cycle, and if you take a cycle and a co-boundary, you get a boundary. If you take a boundary and a co-cycle, you get a boundary. So you don't want boundary getting mapped to cycle or vice versa. So yeah, so this map is scale linear in each variable. And now we should write the relative case. again follows from the same logic. So yeah, basically you want to take a boundary and you should land up in a boundary. You take a cycle and a co-boundary, you should land up in the boundary because co-boundary is modulo something, and so on. So there's almost no content in it, but you have to write it down to understand what essentially it means. So now we come to an important diagram, and it is just if you have a map between two spaces, say x to y. So we want to talk about the group homomorphisms. How do they interact? So if you're given a map f from x to y, you have two group homomorphisms. You have f star, f lower star, which maps homology groups, and then you have another map f upper star, which talks about cohomology groups. Yeah, so this map is f star, and then cohomology map always goes in the opposite direction. If f is from x to y, then f upper star always goes in opposite direction. So we have the cap product, which was induced from what we had written on previous slide. And again we have this map f star as a subscript. So just complete the diagram, we have f here. So this is what we get essentially as a result of what we had done in the previous slide. You take element alpha here and take element phi here, and now just start applying the maps. So you get f upper star phi here, take the cap product, and similarly we do with the bottom part. So after this I want to talk about Poincare duality, and we have to recall what is a fundamental class of a manifold. So the fundamental class of a manifold is nothing but element of the homology group associated with the entire manifold, and this element is such that it matches to the units. From this element you have a map to the unit of other homology groups which are associated to every point of the manifold. Yeah, so Poincare duality concerns fundamental class of a manifold, and fundamental class is nothing but an element of the homology group associated with the manifold, but this element via some homomorphisms matches the units of homology groups associated with particular points. We have seen this before, so this is just a recap. So obviously it has to be a R orientable manifold, only then we can define a fundamental class. So you start with a closed R orientable manifold, and in that case you have the fundamental class, which we know for an orientable manifold how we constructed. We took local orientations, glued together these local orientations via a ball, and then we glued these balls together to obtain the manifold. So it is nothing but an element of this homology group. So you are taking just one element of the homology group and call it alpha, and then you have the following map. Yeah, so we have already seen this map coming from the cap product. So M cap alpha, and this map is an isomorphism for all k.